Our next speaker is Akshay Krishnamurthy.
Okay, thanks. This is joint work with Dylan and Haipeng. Dylan is here, Haipeng ran off. It's about model selection for contextual bandits. So let's start off by recapping one type of model selection result from statistical learning. This is something I learned my first year of grad school. So you have a data set of XY pairs that are drawn IID from a distribution D. You have a nested sequence of function classes, script f1, script f2, script fm. They're contained within each other. And for now, let's just assume the Bayes optimal predictor f star lies in script f sub m star for some class m star. So using an algorithm like structural risk minimization, you can find a predictor f hat n from these n samples whose excess risk scales with the complexity of the class script f m star divided by n, and you pay a little bit more for doing model selection. But the point here is that the excess risk scales only with the class m star and not with the much larger, potentially much larger class capital M. And this is, you can get this from structural risk minimization. So the question we're asking here is, can we achieve the same kind of guarantee in an online partial feedback setting? So the first thing to note is actually it's very easy to achieve this guarantee in the online setting. The difficult part is doing both online and partial feedback. Okay, so to set the stage, we'll make things a little concrete by assuming linearity. So I'm going to consider linear contextual bandits. So the game proceeds for t rounds. In each round, you observe a context xt, you take an action at, and you incur some loss for your action. And the loss for this action is the only thing you observe. The regret is measured as the sum of your losses minus the sum of the losses of this policy pi star, which I will define very shortly. And we're going to be in a linear setting with many different feature maps. So you have these feature maps phi m, one for each, m goes from 1 to capital M. And these map the context action pairs into dm dimensions each. So the dimensions are going to be increasing. We're also going to posit realizability. So there's some weight vector theta star in some dimension dm star, which is for which the losses are realizable. So the losses are linearly related to this feature map phi sub m star with this parameter theta star. Okay, and the optimal policy uses this unknown coefficient vector theta star and this unknown parameter feature map phi m star to select his actions. Okay, and just to make it clear, if you knew m star beforehand, you could just run this algorithm called linucb using the feature map phi m star, and you could get this kind of regret, d square root dm star t log k. This is kind of classical, maybe. Okay, so this is the setting. So we're going to consider this problem where you don't know m star. And what we get is, without knowing m star, we get regret t to the 2/3 dm star to the 1/3. This algorithm that we have, you can also retune it in some other ways, so you can get square root t dm star plus t to the 3/4. I'm suppressing k dependencies here. Well, they're on the slide, but I'm not going to say them. This is in a stochastic setting. There's some technical assumptions required. You might think this is kind of bad. I buy it. The one thing I will say is that this shows that model selection is possible whenever the problem is learnable. So the linucb guarantee is non-trivial whenever d is little o of t, and so are these guarantees. On the other hand, of course, I would hope you can get square root t regret, and we don't know how to do it yet. So let me just tell you a little bit about how we do this. The key idea is actually to estimate the square loss gap between two classes. So let theta I star and theta j star be the optimal predictors using feature map phi I and phi j. So this is the square loss gap between them. And naively, you could estimate this using a plug-in estimator. So you estimate theta I star using least squares, you estimate theta j star using least squares, and you just evaluate this quantity. So we show that you can actually do much better than this. So we have an estimator that has a square root d dependence here. And this is actually related to what Brian was just talking about. This is sort of one of these sublinear estimation type things. And it refines some results by Wei Hao, Kong, and Greg Valiant, and Dicker. And then the algorithm is very simple. You run a contextual bandit algorithm with this small class, di. You mix in some exploration. Using the exploration, you can estimate this, this square loss gap. And if you find that it's non-zero, you switch to the higher dimension. Cool. So that's about it. Let me just summarize. So we have this is actually the first model selection guarantee that I know of for contextual bandits. The key technique is fast rates for estimating square loss gap. There's a recent paper on arXiv by Niladri, Vidya, and Peter that does something kind of similar. And I think an interesting open question, which I actually don't know the answer to, is whether we can get root DT regret for all D without knowing M star. Thanks, and that's a link to the archive paper.
Questions for Akshay? Yes.
How does your bound depends on M, capital M?
Yeah, so you can basically make it logarithmic. There's some tricks to say capital M doesn't really matter. Yeah, yeah. But I don't think we're getting little m star, we're getting log capital M. Yeah.
Please go to contextual bandits, because for that specific case of smaller dimension contextual bandits, there are already results of sketch contextual bandits that get the smaller dimension by doing explicit sketching instead of model selection.
But in the,
Essentially, it's possible to have a linear contextual bandit projected in a smaller dimensional space and get the right regret.
but you might not be realizable anymore?
Well, there are ways to state that. But I mean, this is more general because you can really select among possible models.
I see.
That one constructs a model that's realizable. So
I see, okay. Yeah, I'll talk to you about it after.
Let's
Okay.
keep
Yeah.
discussions
Yeah.
later. Okay, let's thank the speaker again.